Hi, I'm Xipeng. This video will present my master thesis named Linked Urban Data. In urban planning, the lack of dynamic data at the early stage of planning can lead to poor design decisions. For example, oversight or not taking into account of the traffic flow or volume. It can negatively impact planning, which would resulting in unreasonable pathway, incorrect parking or building locations, flawed program distribution, or excessive traffic, and the underserved public transportation. A main challenge to make more informed data-driven decisions is that data are come from different platforms, and it is present in completely different field format, representing different aspects. This means that data are disconnected and rarely linked. There are various approaches to data modeling. Relational databases work well with structured data, but they become difficult to use when handling complex relationships. XML is good for hierarchical data format, but it is limited when adding new information or data that we change or update. On the other hand, knowledge graphs enhance data representation. They allow data integration from multiple sources, as well as allow reasoning and derive new knowledge. Such structured data is suitable for complex query answering and can also provide a good structure for machine learning models. They are also a data modeling of semantic web standards. So, what is semantic web? Semantic web technologies are one of the strategies to connect data, and is an approach that has been used computer science. In semantic web technologies, knowledge graph and ontologies help to structure the data. An ontology is a formal description of knowledge as a set of concepts within a domain and the relationships that hold between them. Just like a theory of knowledge of Plato, ontology is a study of what exists plus the taxonomy, the classification of the object, which puts them in context. A knowledge graph is a graph-structured database which would hold in two parts. First, the ontology, which is reusable. The schema of the data, also be called T-box. And second, the assertion, the project specific data, we also call it A-box. Here is an everyday example. Site is the terminological data, while Ubak Tower is the project-specific data. So, what can a knowledge graph do with this? It can connect multiple databases, in this case 3, highlight in different color, and can run through them all to answer a more complex query, such as which site was visited by the dean of university, which has a study program where I was studied in. In the scope of this project, I will analyze existing ontologies, extend them, and use them to represent Stuttgart's static and dynamic urban data. The formed knowledge graph will be used for urban data analysis. For urban designer to use this ontology, I purpose a 3-step workflow. First, collecting the data and parsing the data to the ontology. The final one is link static and dynamic data for analysis. In the scope of this thesis, the data that I work with is morphology data from OpenStreetMap, traffic flow data, and public transportation data. From the OSM ontology, I check the tagging system containing key value pairs. For my research, the most relevant tags were highway and building. Therefore, a next step, I select relevant information related to the morphology of building and highway. I also define some alignment between the OSM and Urban Dynamic Ontology, shortly UDO. To do this, I use the web ontology language semantics. This approach allows for the creation of relationships based on the location information provided by different datasets. The OSIM as attribute is used to link identical entities. And as a method to link data and apply reasoning on it, I suggest using OReasoner as well as query language, which I will demonstrate in the development part of my presentation. I will demonstrate the application of the method with Stuttgart as a case study with 3 different user scenarios. The use cases are based on the data we have. Urban morphology data are from OSM library. Traffic flow data are from UTD-19, the largest multi-city traffic dataset. And the past public transportation are from VVS Stuttgart. They have the urban transportation data, which include routes, trip, and stop information. The total volume of data exceeds 1 million nodes and can be officially classified as big data. However, this data is not linked. To be able to question cross-database queries and integrate this data, I will use developed ontology, build one single knowledge graph unifying all 3 datasets. Now, for the knowledge graph generation of morphology data, I developed a converter that can take OSM CSV data and convert them to graph using turtle serialization. Similarly, with the past public transportation data, I use the same pairs from CSV to turtle based on the developed ontologies. And the same follows for the traffic volume data. To link the graph of different databases, we use their spatial information. I divided OSM road into segments and found the VVS station and the traffic volume detectors. Based on their geographic coordinates, and found the nearest roads for each building on the map. So, as a result, all buildings were associated to a street. Each street segment has a traffic volume count and bus stops as well. I then test the now interconnected data graph on 3 scenarios represented by different users and urban designers or planners, municipality officials, and a real estate developer with different aims. In the same way, different strategies can be turned into measurable indicator. For example, a site with a capacity of 200 people can be checked by the size of the open space and the open space ratio. To find an answer, we need to run multiple queries that use Connect database. We can start simplify by sorting from lowest to highest traffic volume location that include an empty plot within 600 meters radius. Then add an area requirement of the empty plot as well as and sort again. Then retrieve all building of the area. And check what building program are around of this empty plot. then calculate and sort the result based on the open space ratio and the mixed-use index of the area. To check how many public transportation lines run in this area radius, we first get all public transportation lines and stop locations around the empty plot, and then sort from highest to lowest number of public transportation routes, and sort based on the route's frequency to determine the accessibility. The queries give us some potential area, and it looked like the top 5 most suitable locations for Stuttgart New Vibrant Park. And they're a bit outside of Stuttgart. Of course, if we add the population data such as density and integrate other urban data, the result might be difficult. City officials aim to improve public transportation. One of the strategies to increase the bus frequency, affecting waiting times and route incidents. Key parameters include arrival-departure time and route coverage. However, some data are not available. A real estate developer was looking for a plot of land in Stuttgart for the building of a new hospital. The first step is to identify the area with no medical facilities. This will affect the indicator, distance to the nearest medical facility, and the land use catalog. Data on the distance to the nearest medical facility is therefore crucial for the assessment. The developed framework can be integrated into design software or as a standalone web application. However, this is beyond the scope of my thesis. In any case, I have developed a mock web interface to give an idea of how to interact with it. For example, a real estate developer selects the right user profile, selects the area of their search, and select from a list of predict questions. I'm a bit fast. They can input the square meters for their search. The system generates text and displays the result on a map that the user can click to view the details. The tagging system can search beyond the predefined question to provide information, such as traffic flow and road width, to help with the site selection. Search results are saved as text and be compared via graphically for easy analysis and presentation. In conclusion, I have formalized a new ontology for dynamic traffic data and developed a workflow that links this data with static morphology data from 3 datasets. Additionally, the methodology can be extended and the framework adapt to other type of data or to include more datasets. And that is my master thesis. Thank you all for listening.